In this video, we are going to solve a simple thermodynamics problem that contains a vessel with rigid walls. Let's begin. A rigid tank with a total volume of 0.5 meters cubed contains propane. Based on manufacturer's information, the vessel can rupture when the pressure reaches 30 bar. If the vessel is heated up to 400 Kelvin, calculate the amount of propane in the tank such that the pressure only reaches 15 bar. Alrighty, so let's talk about the important information. We have propane. So we'll be using the propane tables. We also know that this vessel has a total volume of 0.5 meters cubed. So that's how much volume it holds. Volume 1, 0.5 meters cubed. If the vessel is heated up to 400 degrees Kelvin, so it's going to be heated up to 400 degrees Kelvin. We need to calculate the amount of propane in the tank such that the pressure only reaches 15 bar. Alrighty, so P2 is going to reach 15 bar already. So this is like the important information that we have, right? This is a closed system problem because there's no mass crossing the boundaries. So closed system means that the mass at the beginning is the amount of mass that we have at the end, which makes sense. It's a closed vessel. The amount of propane in it, the mass will be the same before and after it was heated to 400 degrees Kelvin. And we also know that it's a rigid tank. It tells us in the problem. If it's a rigid tank, that means that the volume at the beginning is going to be equal to the volume at the end. And since M1 equals M2 and V1 equals V2, it means that since it's a closed and a rigid tank, it means that the specific volume at the beginning is equal to the specific volume at the end. And that's a really good piece of information because these are values that we can find in our tables. Okay, so our plan, let's write our plan. Our plan is to first find the state. Find state, which we can do because they give us the temperature and the pressure. So we can go ahead and figure out if it's superheated or compressed or if it's a saturated mixture. Then we're going to find V2 or a specific volume. And the reason why specific volume is really important because what we're trying to find, right, is how much propane, the amount of propane in the tank. So we're trying to find mass. And specific volume is equal to volume over mass. So if we figure out volume, if we figure out the specific volume, since we already have the volume, we can find mass, right? Because and so we found specific volume, and then we're gonna find mass, and we can do that because from this equation, mass is equal to the volume divided by the specific volume. So great, let's go ahead and start and find our specific volume in order to answer this question. So first part of the plan is to find the state. These are the rules or the little cheat sheet as to how to find the state of propane. So what we're going to do is we're going to look up P, or the pressure or the temperature, in the saturated propane tables and then compare. Alrighty? So I'm going to go ahead and open up that table. So first thing is look up where the pressure is equal to 15 bar in table 5.12, which in my textbook it's the properties of saturated propane. And this is the pressure tables. Okay, so I'm going to go ahead and open up the table 5.12 and look up where the pressure is equal to 15 bar. Alrighty, so we open up our textbook, table 5.12, and we look for pressure at 15 bar. I see that the pressure at 15 bar right here, found it. The temperature that would make propane saturated at a pressure of 15 bar will be 44.01 degrees Celsius. Alrighty, so we're going to go ahead and compare that number, the 44.01, to the temperature given in the original problem. Alrighty, so let's see what we have here. We saw that our T saturated, or temperature of saturation at P equals 15 bar, was 44.01 degrees Celsius. Alright, and we're going to go ahead and make it into Kelvin by adding 273.15, and we get 317.16 Kelvin. The T given that we got from our problem was 400 degrees Kelvin, right? That's the temperature of propane. So the T, or temperature saturated, is less than the temperature given. And if we look at our cheat sheet, we see that when the temperature, the saturated temperature, when it's less than the temperature given, it's a superheated vapor. So our propane right now is a superheated vapor. And since it's a superheated vapor, we are going to find the specific volume in the superheated propane tables. Not the compressed liquid one or the saturated one, but the superheated propane tables. So the next part of our plan was to find V2, or find specific volume. And our table that has superheated propane in it is table 5.13, and it's called Properties of Superheated Propane. And to remind ourselves what our temperature given was, it was 400 degrees Kelvin, or 400 Kelvin. And our tables in the textbook that I have, the table 5.13, the temperature is given in Celsius. All of those values are Celsius. So I'm going to go ahead and convert Kelvin into Celsius. So we're going to subtract 273.15, and we get 126.85 degrees Celsius. And then reminder, our P given was 15 bar. And again, my tables are in kilopascals, not bar. So I'm going to convert it into kilopascals. Great. And now we look for the specific volume in our table. I cut off the titles of each column. So this column is a specific volume. This one's internal energy. This one's enthalpy. This one's entropy. So, and the same thing on the other side. Okay. So I'm looking for superheated propane at 126.85 degrees Celsius and at 1,500 kilopascals. I see here, and we don't have information when the pressure is equal when the pressure is equal to 1,500 kilopascals. However, we do have information for 1,400 kilopascals and 1,600 kilopascals. So we're probably going to have to do some sort of interpolation in order to figure out those values in between. And also, unfortunately, we are not given the temperature at 126.85 in our tables. So we're going to actually have to do double linear interpolation in this case. So again, we don't have the 15 degrees or 1500 kilopascal tables, so we're going to have to interpolate for that. And we also don't have temperature at 126.85, so we're going to have to interpolate between these two guys for the value of 126.85 degrees Celsius. I'm going to go ahead and take note of all the numbers I'm going to need for double interpolation. I'm going to need my bounds, my upper and lower bounds, plus the actual place I want to look for, and then same thing for the temperature, upper and lower bounds, plus the actual value I'm looking for. And since we're looking for a specific volume, we're going to be looking at this guy, that guy, and also this guy and that guy, right? Alrighty, so I'm going to go ahead and set up my double linear interpolation with this table right here. So my x1 or my y1 is going to be 120, right? My lower bound or whatever. And then I'm looking for 126.85, and then my upper bound is 130, right, for my temperature. And then for my pressure, my lower bound is 1400, so that's my x1. My x is going to be 1500, and then my x2 is 1600. Great. So essentially, I'm looking for this guy right here, right? I'm looking for P. So in order to find P, I still need all the other values that surround it. So at 1400 kilopascals and at 120 degrees Celsius, the value that is there is 0.04774. Again, you can just look it up on the table. It's right there. And then the value at 1400 kilopascals and 130 degrees Celsius is that one, 0.04942. And then same thing on this other side at 1600 kilopascals and 120 degrees Celsius. The specific volume is 0.04107, and at 1600 kilopascals and 130 degrees Celsius, the specific volume is 0.04259. And now we double interpolate to find our P value. You can go ahead and plug everything in to this equation right here, or you can look up an online calculator, or you can code it into your own calculator or use Excel. Really, whatever, it's up to you and whatever your teacher lets you use. So just in case, this Q11 represents that number right there. This Q21 represents that number right there. Just so to make things extremely clear. Alrighty. If you were to do all of your interpolations correctly, you get that our green P, right, the specific volume at 1500 kilopascals and 126.85 degrees Celsius is 0.045501. So again, specific value of 0.045501 meters cubed per kilogram. Because those are and that's because if I wouldn't have cut it off, those are the units that were mentioned in my table. Alrighty, however, we're still not done yet because we're looking for mass. And we know that mass is equal to our volume divided by our specific volume. And when we plug everything in, so remember our original volume is 0.5. So 0.5 meters cubed divided by 0.045501 meters cubed per kilogram will give us the value of 10.99. So the amount of propane that is in that vessel is 10.99 kilograms. Yep. That was it for this problem. It's a pretty simple thermodynamics problem, but they do get harder, but it's important for you to understand how to use tables because that will be your base to all other thermodynamics problems. I hope you learned something, and good luck with your studies.